Welcome to this comprehensive lesson on redox reactions for IB Chemistry Higher Level. In this lesson, we will cover oxidation and reduction, oxidation states, balancing redox equations, electrochemical cells, standard electrode potentials, and electrolysis. Let us start with the fundamental definitions. Oxidation is the loss of electrons. When a species loses electrons, its oxidation state increases. Reduction is the gain of electrons. When a species gains electrons, its oxidation state decreases. A helpful mnemonic is oil rig: oxidation is loss, reduction is gain. For example, when magnesium reacts with oxygen, magnesium loses electrons and is oxidized. Magnesium becomes magnesium 2 ++ 2 electrons. Oxygen gains electrons and is reduced. Oxygen plus 4 electrons becomes 2 oxygen minus ions. The oxidation state, or oxidation number, is a concept that helps us track electron transfer in redox reactions. Here are the rules for assigning oxidation states. First, elements in their elemental form have oxidation state 0. Second, fluorine is always -1. Third, group 1 metals are +1. Fourth, group 2 metals are +2. Fifth, oxygen is usually -2. Except in peroxides where it is -1. Sixth, hydrogen is usually +1, except in metal hydrides where it is -1. Seventh, in binary compounds, the more electronegative element gets the negative oxidation state. Eighth, the sum of oxidation states equals 0 for neutral compounds. Let us work through an example. What is the oxidation state of chromium in dichromate ion, Cr2O72-? Solution: let X equal the oxidation state of chromium. 2x plus 7 times -2 equals -2. 2x minus 14 equals -2. 2x equals +12. Therefore X equals +6. The oxidation state of chromium is +6. An oxidizing agent, also called an oxidant, is a substance that causes oxidation by accepting electrons. It gets reduced. A reducing agent, also called a reductant, is a substance that causes reduction by donating electrons. It gets oxidized. Common oxidizing agents include potassium permanganate, KMnO4, potassium dichromate, K2Cr2O7, chlorine gas, Cl2, and hydrogen peroxide, H2O2. Common reducing agents include metals such as zinc, iron and magnesium, sulfur dioxide, SO2, and iron 2+ ions. There are two main methods for balancing redox equations: the half-reaction method and the oxidation number method. Let us learn the half-reaction method for acidic solutions. First, write the unbalanced equation. Second, separate into oxidation and reduction half-reactions. Third, balance atoms other than oxygen and hydrogen. Fourth, balance oxygen by adding water molecules. Fifth, balance hydrogen by adding hydrogen ions. Sixth, balance charge by adding electrons. Seventh, multiply half-reactions to equalize electrons. Finally, add half-reactions together and cancel common terms. Let us work through an example. Balance the following redox reaction in acidic solution: permanganate ion plus iron 2 plus produces manganese 2 plus plus iron 3 plus. First, write the oxidation half reaction. Iron 2 plus goes to iron 3 plus plus electron. Next, the reduction half reaction. Permanganate ion plus 8 hydrogen ions plus 5 electrons produces manganese 2 plus plus 4 water molecules. Now multiply the oxidation half reaction by 5 to match the 5 electrons. 5 iron 2 plus goes to 5 iron 3 plus plus 5 electrons. Finally, add the two half reactions together. Permanganate ion plus 8 hydrogen ions plus 5 iron 2 plus produces manganese 2 plus plus 4 water molecules plus 5 iron 3 plus. The equation is now balanced. An electrochemical cell converts chemical energy into electrical energy through redox reactions. The main components are two electrodes called the anode and cathode, an electrolyte solution, a salt bridge or porous membrane, and a voltmeter to measure the potential difference. The anode is where oxidation occurs. In a voltaic cell, it is the negative electrode. The cathode is where reduction occurs. In a voltaic cell, it is the positive electrode. We write cell notation in the form anode, vertical line, anode electrolyte, double vertical line, cathode electrolyte, vertical line, cathode. For example, the Daniell cell is written as zinc solid, vertical line, zinc 2 plus aqueous, double vertical line, copper 2 plus aqueous, vertical line, copper solid. Standard electrode potential, denoted E0, is measured under standard conditions. These are 1 mole per decimeter cubed concentration, 1 atmosphere pressure for gases, and temperature of 298 Kelvin. The standard hydrogen electrode, or SHE, is assigned a potential of 0 volts and serves as the reference for all other measurements. To calculate the cell potential, use the formula E0 cell equals E0 cathode minus E0 anode. Let us work through an example. Calculate E0 cell for the reaction, copper solid, vertical line, copper 2 plus aqueous, double vertical line, silver plus aqueous, vertical line, silver solid. Given standard potentials are E0 of copper 2 plus / copper equals plus 0.34 volts. E0 of silver plus / silver equals plus 0.80 volts. Using the formula, E0 cell equals E0 cathode minus E0 anode. Substituting the values, 0.80 minus 0.34 equals plus 0.46 volts. A positive cell potential indicates the reaction is spontaneous as written. Remember, if E0 cell is positive, the reaction is spontaneous. Electrolysis uses electrical energy to drive non-spontaneous redox reactions. Key concepts include the electrolyte, which is an ionized substance that conducts electricity, inert electrodes such as platinum and carbon that do not participate in the reaction, and active electrodes that do participate. Factors affecting electrolysis include the nature of the electrolyte, concentration of ions, type of electrode, temperature, and current and time. Let us look at the electrolysis of aqueous sodium chloride, also known as brine. At the cathode, water is reduced to hydrogen gas and hydroxide ions. 2H2O plus 2 electrons gives H2 plus 2OH minus. At the anode, chloride ions are oxidized to chlorine gas. 2Cl minus gives Cl2 plus 2 electrons. This is the chlor-alkali process. Industrial applications of electrolysis include the extraction of aluminium from bauxite, purification of copper, electroplating, and the chloralkali production of sodium hydroxide and chlorine. Let us look at some practice questions on redox concepts. Question 1. Which of the following equations represents the enthalpy change of atomization for bromine? Remember, atomization involves forming 1 mole of gaseous atoms from the element in its standard state. Question 2. Which compound undergoes oxidation when heated with acidified potassium dichromate? Think about which functional groups can be oxidized by dichromate ions. These types of questions regularly appear in IB chemistry examinations. To summarize the key points of this lesson. First, remember the mnemonic oil rig: oxidation is loss, reduction is gain. Second, oxidation state rules help us identify redox reactions and balance equations. Third, the half reaction method is essential for balancing complex redox equations. Fourth, a positive E0 cell indicates a spontaneous reaction. Fifth, electrolysis uses electrical energy to power non-spontaneous reactions. Remember to always check your oxidation states and balance both atoms and charge. Thank you for watching this lesson on redox reactions. Practice the worked examples and past paper questions to master this topic.